in order for you to fully understand why integration works, you need to understand the fundamental theorem of calculus 1 and the fundamental theorem of calculus 2. But in order for you to understand these two, you need to understand lots of other bits. You need to understand this, you need to understand this thing here, you need to understand some other bits, you need to understand this thing here, and one of the other things that you need to understand is the mean value theorem, which we're going to look at in this video. So the mean value theorem, so this is the textbook's definition of the mean value theorem. So let me just quickly explain this. So this block here, so if you look at b, if you put it into the function, f of b will jump to here, and then f of a would jump to here. So if you this block here is saying the average gradient of that function in between a and b. So what that means is that's the gradient of that purple line there. Because if you get the height here, what is this height? Well, if you get this height divided by the base, it will give you the gradient of that diagonal line. So what is this height here? Well, this height here would be f of b take away this height here, f of a. So this height here is given by f of b take away f of a, which is this bit here. So that's the height, and this is the base here. What's the base here? It would be b take away a. So you divide it by that length, b take away a. Then this collectively represents the gradient of this diagonal line. And what this is saying is that there exists at least one c somewhere in between a and b. We don't know where, and we don't really care. There exists a c somewhere. When you put it into the f prime, not f, but into the f prime, which is a gradient, then the gradient at c will be the same as the gradient as the average gradient. So for example, hang on. So for example, this is your gradient. This diagonal line here, you can work out the gradient of that. If you draw lots of parallel lines, you see right here, at this point here, which we're going to call C1, if you put C1 into f prime of x, then at this point here, it will have the same gradient as this diagonal line. And so, hang on, there also exists another c for this function. So if you draw lots of parallel lines, hang on, lots of parallel lines, you see at this point here, which we are going to call C2, the gradient at this point would be the same as the average gradient. So that's what the theorem is saying. It's saying that no matter what function you give me, as long as it's continuous and differentiable, no matter what function you give me, the average gradient, there exists a c somewhere between a and b, where the gradient of the function, the gradient of the line itself, will be the same as the average gradient. So let me give you an example. Hang on, let me give you this example here. Hang on. So let's look at f of x equals x squared for the interval 1 to 5. So if you look at this diagonal line, what is the gradient of this diagonal line? Meaning, what is the average gradient in between 1 and 5? Well, to work out the average gradient, f of b would be 25. So 25 take away. So this height here, hang on. This height here is given by this, and the width here is given by 5 take away 1. So this block here represents the average gradient, meaning the gradient of that diagonal line. Well, the average gradient, because if you're here, the gradient will be shallow. If you're here, the gradient is very steep. So the average gradient happens to be this block here, which turns out to be the number 6. So the average gradient is 6. What the theorem is saying is that there exists a c somewhere between 1 and 5 where there must be where the gradient must also be 6. there exists a c somewhere between 1 and 5 where the gradient is also 6. So let's try and figure out where that c may be. So so to do that, you would look at the actual function itself, find f prime, so differentiate it. That will give you 2x, and then this thing here gives us the ability to work out the gradient anywhere along here. But because we want to find the location of where the gradient would be 6, we are going to put 6 into f prime, and then divide both sides by 2. So at x equals 3, you see this is our c here, which happens to be the number 3. You see at x equals 3, right here, f prime of 3 is the same as our average gradient. So right here, the gradient is also 6. At 3, the gradient will also be 6. So let me illustrate it in Desmos. Hang on. So in Desmos, so this is our point here. 5, it would be 25. 1, it would be 1. So our gradient for the green line, for our diagonal line, is 6. So that's this 6 here. The gradient is 6. You see, when I move, when I move it down here, you see right at 3. Right at x equals 3, that's our c there. The gradient at x equals 3 will also be 6. So the theorem is saying that there exists a c somewhere between 1 and 5 where the gradient will be the same as the average gradient, and it happens to be 3. Okay.